Today, we want to look at solving trigonometric equations and the weirdness that goes along with it. I think too often we think about solving equations in math and we break it up into different kinds of equations and all the weird niche techniques that we have to apply, depending on what we happen to be looking at the time. Rather than trying to come up with one overarching principle, and then looking at the weirdness that goes along with each of our niche problems. So here's what I mean. My big idea for solving equations in general, is by performing inverse operations in reverse order. That's the big thing that I want to get across. So my idea, solving equations solve an equation by performing inverse operations in reverse order. Sometimes we get to deviate from this plan. Sometimes we have to abandon this plan entirely because there's too many instances of the variable. But the big idea is we want to solve an equation by performing inverse operations in reverse order. Most of you do not have your background in my algebra class where this is kind of the way I go about things, for good or ill. And so here's what I mean. If we have an equation that says x plus 3 is equal to 7, start with an easy one. We should just be able to solve this by looking at it. If we remember our addition and subtraction facts, how addition and subtraction are related. X plus 3 is equal to 7. That means x is equal to 7 minus 3. So x is equal to 4. Or we can think about doing the same thing to both sides. We subtract 3 from both sides. 7 minus 3 is 4. Both of those paths lead to the same thing. 7 minus 3 is what we need to find. I want to think about piling on extra stuff on the x side. So what happened is that we added 3. This says take x and then add 3 to it. So the inverse of adding 3 is subtracting 3. So we're thinking the inverse of adding 3 this fits in. This is not something new. This fits in with the way that we already solve equations. However it is you solve equations. The inverse of add 3 is subtract 3. So to solve, we would say x equals 7 minus 3. We do the inverse operation, and that leads us to 4. And we know a lot of these things already. So if I have 5x is equal to 15, the inverse of multiply by 5 is divide by 5. The inverse of multiplying by 5 is dividing by 5. So 5 times something is equal to 15. So that something is 15 divided by 5. If we have, or keep going, there's other operations. So if I have an equation that says x to the third is equal to 21, the inverse of a raised to the third power is raised to a reciprocal exponent. The inverse of an exponent is a reciprocal exponent. The inverse of an exponent is a reciprocal exponent. So the inverse of to the third power is to the 1/3 power. The inverse of raising something to the third power is raising something to the 1/3 power. So to solve for a vase, we would take 21 and raise it to the 1/3 power. I need a machine for this because we get an irrational number. 21 is not a nice power of 3. So I'll just wake my calculator up after a week. 21 to the 1/3 power, 2.759. We'll round to the nearest thousand. Now we have to start getting into the weirdness of what's going on here. Some of you might be thinking, wait a second, I thought the inverse of a cube was a cube root. And I said, that's exactly what I said. It's a reciprocal exponents. Fraction exponents are radicals. So reciprocal exponents. If our reciprocal creates a fraction, fraction exponents are radicals. Fraction exponents are radicals. So the inverse of a third power is a cube root, because a cube root is the same as a 1/3 power. If I say, so I could say x is the cube root of 21, which is, let me grab our calculator and go into the math menu and find the cube root of 21. And it's the same, 2.759. So the inverse of an exponent is a reciprocal exponent is a little more general than saying the inverse of a cube is a cube root. Once again, try to factor things out. Try to look at what's the same versus what's different. Sounds like good advice in general. Look at what's the same, not for what's different. And then behave rationally, which is the hard part. So we're starting to fill in some of the weirdness. If I have an equation that says, for example, the cube root of x is equal to 2, we know that a cube root is a 1/3 power, and so we can use the general rule. The inverse of an exponent is a reciprocal exponent. I can read the cube root of x equals 2 as the equation x to the 1/3 is equal to 2. So to solve, I would say the inverse of a 1/3 power is the reciprocal of a third, which is 3. So I'd solve x is equal to 2 to the reciprocal of 1/3, which is 3, which is 8. Because radicals are fraction exponents. For those of you still on the radical train, because you like archaic notation, I mean, that's cool. I like archaic notation too, but it kind of makes more sense to use fraction exponents. Because what we're doing is we're still taking both sides to the 1/3 power. If I have an equation, an expression that says x to the third, and I raise that to the 1/3 power, and I think about doing this to both sides of the equation, because we always like to say, do the same thing to both sides, but then we need more details, what things to do, and in what order do we do them. When we raise an exponent to an exponent, we multiply the exponents. 3 times a third is 1. 3 times 1/3 is equal to 1. So what we have is x to the first is equal to 21 to the 1/3 power. And to me, this makes a little bit more sense than the cube root, because we don't often read the cube root as a 1/3 power. But now it fits in with the way we think of exponents. We've expanded how we understand exponents to include these things called radicals. And we've got a more coherent system. We're looking at all the things that are the same. So all these equations had just one operation in them. And I said, perform inverse operations in reverse order. So let's look at an equation that has more than one operation. Let's suppose I have x cubed minus 5 is equal to 21. Let's look at the things that happened to x. How did x become 21 in the story of this equation? What operations turned x into 21 in this story? We started off with an x and eventually it became a 21. How did this happen? Well, the order of operations says the first thing that happened to the x is a 3rd power, because exponents go before addition and subtraction. After we got the 3rd power of x, we subtracted 5. Once we know the story of how x turned into 21, we can just follow this backwards to turn 21 back into an x. So if we want to turn 21 back into an x, we do inverse operations in reverse order. So first, we'll take the 21 and we'll do the inverse of subtracting 5, which is add 5. And second, we'll do the inverse of to a 3rd power and raise to the 1/3 power. So I'll take my 21 and I'll start off by adding 5 to it and come up with 26, and then take my 26 and raise that to the 1/3 power. And I need my machine. Should have gone with 16 so I'd have this number, but I don't. So I take the 21 and I first added 5 to it. And then I'll take my 26 and raise that to the 1/3 power. And we get 2.962. So then I report my answer, x equals 2.962. Or if we need an exact value, we could say it's the cube root of 26. Now at this point, you're thinking, dude, is this not a trig class? Where are the trig functions? To which I'll respond, hey, don't call me dude. Actually, it's totally okay. This is California, so it makes sense. But we're getting to that. The idea is that when we want to understand a function and we want to use that function in equations, we have to understand that function's inverse. Before we get to the trig functions, I just wanted to remind you that trig functions are a thing and that we will be getting to them. I want to look at when we have extra stuff. What happens when there is extra stuff in your inverses? So for example, let's suppose instead of x cubed minus 5 equals 21. Well, actually, let's look at a simpler example. Let's look at the equation x squared is equal to 25. Now, we could think of solving this by just doing square root of both sides or raise both sides to the 1/2 power. But here's the thing that we notice. The function here, x squared, is not technically invertible because it doesn't lead to one answer. There are two numbers such that when we square them, we get 25. This equation has two solutions. This equation has two solutions. Oh my gosh, two real solutions. And the weirdness continues. But this equation has two solutions, two real solutions, because there are two numbers such that when you square them, you get 25. 5 squared is 25, and -5 squared is also 25. Two solutions. 5 squared is 25, and -5 squared is equal to 25. Your calculator will only tell you one of these solutions if you just do a 1/2 power. If you ask your calculator what the square root of 25 is, you're not asking your calculator to solve the equation. You're asking your calculator the specific question, what is the square root of 25? And that is 5. Because if we want the negative one, we have to specify that we want the negative one. Or in this case, the -5. So your calculator is not actually solving the equation x squared equals 25. We're asking the calculator what's the square root of 25 and using that to solve the equation. Because calculators don't understand human language. Calculators are kind of dumb that way. My calculator's like, oh, hey, I heard that. I've heard you say that before. And it kind of hurts my feelings. I'm just kidding. It's a TI-84 plus. It doesn't have feelings. That hurts my feelings. I'm just kidding. My calculator's not talking. That's what they tell me. They tell me it won't talk to me. And then I'm making that up. So there's extra stuff in our inverse. So we have to recognize what functions have this extra stuff that's going on. So what happened in the equation is that x turned into a 25, and the operation was we raised to the second power. So that when we do inverse operations to turn a 25 back into an x, we can think of doing a square roots or a 1/2 power, but we have to recognize that a square root could have two solutions, two real solutions. We have to bring that knowledge to the table ourselves. We have to know that an equation with an even exponent could have 2 or 0 solutions. Not one, but 2 or 0 solutions. It could have one, but then it'll be very clear. That's something that we have to know. The machines don't tell us that. We have to know that extra stuff. The machine will deliver us the 5. We have to remember that there's also the -5. What this means is that when we're solving, if this squared operation shows up in the middle, if there are more operations to perform afterwards, we have to do that to two solutions. So for example, still not at trig stuff. If I have the equation say x minus 3 squared equals 25, when we read the equation, to turn an x into a 25, First, we're subtracting 3, and then we raise to the second power. So that when we go to solve, to turn a 25 back into an x, first, we do a 1/2 power. And this is where we say 2 solutions are going to show up. And then, now we have 2 numbers that we have to add a 3. So I take 25 and raise it to the 1/2 power, and that gets 5 and -5. Because we had an even exponent, and so that means there could be 2 solutions. And then moving forward, I have to take a 5 and then do the +3. But I also have to take the -5 and add 3 to it. So then we can report back our solutions, x equals 8 and -2. 8 minus 3 is 5, 5 squared is 25. -2 minus 3 is -5, -5 squared is also 25. So we had 2 solutions. Any questions? We can reinforce this understanding that there are 2 solutions by imagining what the x minus 3 squared looks like. I'm not sure where you came from in your algebra class, but if we look at a graph of x minus 3 squared, we know that the x minus 3 squared makes a parabola. And it's sitting on the x-axis. And the vertex is at 3, 0. So if this is the graph of x minus 3 squared, I want to know when the graph of x minus 3 squared is equal to 25. And we can see that if I draw y equals 25, this happens in 2 places. There are 2 intersections. One corresponding to x equals -2, and the other one at 8. Notice that the -2 and 8 are both 5 units away from the middle, which is 3. 3 plus 5. And 3 minus 5. That's just utilizing the symmetry in the parabola. So we can't just know, we have to know if our function is going to produce any kind of weirdness. So notice that I specified that there are 2, if x squared equals 25, there are possibly 2 real solutions or 0 real solutions. With the x cubed minus 5, if the exponent is 3, there are going to be 3 solutions. It's just that one of them is real and the other 2 are complex solutions. That's something that we're going to allude to. And then when the DVD comes out, or the Blu-ray comes out, or the digital download comes out, you can download the director's commentary, or the Professor Leach cut of trigonometry, which is like not 17 weeks long, but like 84 weeks long. It's like the Snyder cut, only instead of going from like 2 hours to 4 hours, it goes from 17 weeks to 17 years. So it's just same kind of thing. And really what it comes down to is that someone wants to sell you this movie again. Now, that's really all it comes down to. But remember, in my plan, even though it sounds like just someone trying to make some money, in my plan, if you put me in charge, y'all wouldn't be paying to go to school. I would be paying you to go to school. This would be your job. Because remember, America is a business. If you want people to do stuff, pay them. Could have solved this whole mask problem if you just pay people to wear masks. Could solve the vaccine problem if you pay people to get the vaccine. Could solve the stay-at-home problem by paying people to stay at home. You want people to do a thing? Pay them. That's it. You know what I mean? So like when like, oh, everybody's got to stay home so we can all avoid passing on the virus. And when someone's like, oh, dude, I can't just stay home. I have to go to work to make money. I would be like, oh, how much money would you have been making? And you'd be like, oh, $600. I'm like, oh, here's $800. Stay home. And you'd be like, oh, all right. And then when your boss is like, oh, if he doesn't come in, then I won't be able to make money. I'm like, oh, how much money are you going to be making? And I'm making $10,000. Here's $10,000. Good thing we've been sacking money away. Now stay home. Oh, and that person that I paid to stay home, they still have a job when we can come back from this. And if you don't do that, then I'm just going to take your money away. Simple. If you want people to do something, pay them. And then if you want to play capitalism, don't pay them and argue that you shouldn't. You know what I mean? So we got to watch out for extra stuff in our inverses. So this x squared throws a wrench into this perform inverse operations in reverse order, because an x squared could have 2 real solutions or it could have 0 real solutions. If I said x squared equals -25, all of a sudden there are no real numbers that fit that description. Where do trig functions come into this? See where trig functions come into this. So there are certain things that we know about trig functions. I know, for example, that the sine of 30 degrees is a half. So from a certain point of view, I could say this gives us an inverse function information. I could say that the sine inverse of 1/2 should be 30, and be able to use that in my solving equations. But we know more about sine than just sine inverse on our calculating machines, right? Our calculator will tell us the sine inverse of a half is 30. Or if we're in radians, pi over 6. So our calculator will tell us that value, but when we're solving an equation, we want all the values. So infomercial time, but wait. There's more. Sine of 30 is a positive 1/2. So 30 degrees in the first quadrant will give us a 1/2. But also sine is also positive in the second quadrant. So not only do we get this pi over 6, but we also get 5 pi over 6. From the chat, 5 pi over 6. Credit where credit's due. There's also the 30-degree angle in the second quadrant. There's also the 30-degree angle in the second quadrant, the other place where sine is positive. So if I ask you to solve the equation, sine of theta equals a half, there's not just the 30 degrees, or pi over 6, there's also the 150 degrees, or 5 pi over 6. So when I ask you what the sine inverse of a half is, the answer is just 30, or in radians, pi over 6. But if we're solving an equation, now I want all the values. We're solving. Sine of theta is equal to 1/2. We have multiple solutions. Theta is equal to 30 degrees and also 150 degrees. Oops, I wrote my 0 small. There we go. 30 degrees for the 30 degrees in the first quadrant, and 150 is 30 degrees reference angle in the second quadrant. Now this is if I asked you to solve this equation for theta between 0 and 360, because we know that before 0 and after 360, sine just repeats. It just makes a copy of itself. So this is the equation for theta between 0 degrees and 360 degrees. Because it gets even further, but wait. There's even more. Let's suppose that we wanted to solve this equation, sine of theta equals 1/2 for all values of theta. Now, answering this question will absolutely make all of trigonometry just snap into place. And you'll say, that's it, Leach, we are done. You don't need to explain anything more. You don't even need to bother with the final. We're all just gonna get A's because we could totally see it now, but only if I answer this question right here, right now for you. So once again, if I just answer this right here, right now, all of trigonometry will just instantly snap into place. So here we go. Let's fix trigonometry. It'll be like a download from the matrix. Just like boom, everything will make sense. So here we go. Everything's about to make sense. Oh darn, look at the time. All right, that's going to do it for today. I know there was not a lot of trig stuff and a lot of solving equation stuff, but it's about how we think about things, not just about how we do things. So what I want you to think about for Wednesday is, what more could we add when I change from theta between 0 and 360 to all values of theta? And we're going to think about the graph like this. Think about this graph. And think about the 1/2 running through it. And think about how many solutions there's going to be. All right, that's going to do it for today. Welcome back from spring break. Everybody have a good couple of days. I'll see y'all on Wednesday, and thanks for playing.